Hello, welcome to a video for grade 12 physics. Today we're going to take a look at basic orbits. So let's start with a fairly famous thought experiment. Imagine that you've got a cannon sitting on the ground and pointing horizontally. Now if you fire that cannon, the cannonball is going to take a curved path and hit the ground, something like that. All right, that's fairly straightforward. We've talked about that a lot in our projectile motion unit. Now let's say that I wanted this cannon to fire the cannonball further. Well, one way I could do that is if I had that cannon sitting on top of a tall hill, that same cannonball launched at the same velocity would travel further. It might end up something like that and hit the ground further over here. Now, similarly, if I take this cannon and I want to fire further still, if I fire with an increased velocity here, I could fire my cannonball still further. This is basic projectile motion. We've been doing this for a while now in physics. Now, to make this a little bit more interesting, make this a little bit more challenging, the thing we have to realize is that as I zoom out, the Earth is curved here. The Earth's surface actually starts curving away from the path of the cannonball. So if I look at my cannonball now, this faster cannonball here actually traveled an additional distance to get down to the ground because the Earth was curving away from it. If I fire it still faster, you'll see that the cannonball travels further still or hitting the ground because the Earth's surface is curving away from it. Now, if I zoom out even further to where I've got the entire planet here, so here's the planet of Earth, and let's say that I've got my big mountain here and I've got my cannon sitting on top of it. If I start firing my cannon fast enough, you'll see that it will travel quite a far distance before hitting the ground. If I fire, however, this cannonball fast enough, eventually it misses the Earth entirely and travels back to where it started. So effectively, we fired our cannonball fast enough that we missed the Earth. This is one way to think about a simple orbit. The cannonball is still falling towards the center of the Earth. If I look at any particular point in this cannonball's path, it is still being pulled down towards the center of the Earth. But because it is traveling so quickly, it is missing the Earth. By the time it would fall down to the Earth, it's already further along in its path here. Turns out, this is exactly how we can orbit the Earth. We need to be high enough so that we don't hit the mountains, and high enough so that we're out of the atmosphere, that air doesn't slow us down. Then we need to be going fast enough that we orbit the Earth, we miss it. For example, the International Space Station is an average of 400 kilometers above the surface of the Earth and is traveling at 7.66 kilometers per second. For comparison, that's well north of 27,000 kilometers per hour. Now, one other way to think about our orbits is to remember our circular motion formulas. So if I take a look at this, here I've got a satellite that's orbiting the surface of the Earth. What I can do is I can say, well, here's the satellite going around the Earth. Yay, satellite's going around the Earth. So if I trace the path, you can see that the satellite is happily going along going in a circular orbit here. Now we can also see that the velocity vector of this satellite is tangent to the circle. So if I pause at any point here, the velocity vector is pointing in a straight line from where the satellite is. However, the force is pulling this satellite towards the center of the Earth. You can see the satellite here is being pulled towards the center of the Earth. The force and the acceleration are towards the center of this circle. So in this simple case, we can model an orbit as a circular motion problem where the force is provided by gravity. Now, in later videos in this unit, we're going to look at what provides this force with Newton's law of universal gravitation, and we're going to look at Kepler's laws for more complicated orbits, because orbits in the real solar system are not circles. They're very close often, but they're not perfect circles. Thanks for watching. See you in the next video.